The James Webb Telescope has discovered the most distant known galaxy, which appeared just 290 million years after the Big Bang, a scientific article by a group of astronomers. If the universe were a 2-hour movie, then this galaxy would be its first 2.5 minutes, astronomer Kevin Heinlein. The galaxy is estimated to be 1.6 thousand light-years across, and its mass is several hundred million times that of the Sun. Judging by the data obtained, oxygen was present in the galaxy, while a number of massive stars in it had already ended their existence. We are talking about a galaxy called Judas GSR 14-0. It was first discovered in early 2023, but astronomers took time to confirm the information about the new record. The previous record belonged to the JAMES GSZ 13-0 galaxy, which existed 320 million years after the Big Bang. Discovery of the farthest known galaxy by the James Webb Space Telescope, Judas GSR 14-0. The James Webb Space Telescope, JWST, a marvel of modern engineering and astronomical prowess, has recently achieved a monumental milestone in the field of cosmology. A team of astronomers has reported the discovery of the farthest known galaxy, designated Judas GSR 14-0, which formed just 290 million years after the Big Bang. This extraordinary finding provides unprecedented insights into the early universe and the processes that led to the formation of galaxies. Introduction. The James Webb Space Telescope, launched in December 2021, has been hailed as the successor to the Hubble Space Telescope. With its advanced infrared capabilities, JWST is designed to peer deeper into space and further back in time than any of its predecessors. One of its primary scientific goals is to study the formation and evolution of the first galaxies in the universe. The discovery of Judas GSR 14-0 marks a significant achievement in this quest, pushing the boundaries of our understanding of the cosmos. Background and importance of the discovery. The study of distant galaxies is crucial for understanding the early universe. These galaxies provide a window into the conditions that prevailed shortly after the Big Bang and offer clues about the processes that led to the formation of stars, galaxies, and other cosmic structures. The detection of Judas GSR 14-0, with a redshift of approximately 14.0, places it at an epoch when the universe was only about 2% of its current age. The redshift and its significance. Redshift is a measure of how much the wavelength of light from an object has been stretched due to the expansion of the universe. The higher the redshift, the farther away the object is, and the earlier in the universe's history it existed. A redshift of 14.0 corresponds to a time when the universe was just 290 million years old, a period known as the cosmic dawn. This epoch is critical for understanding the formation of the first galaxies and the reionization of the universe, a process that made the universe transparent to ultraviolet light. The James Webb Space Telescope. An overview. JWST is equipped with a suite of state-of-the-art instruments designed to capture infrared light from distant cosmic objects. Its primary mirror, composed of 18 hexagonal segments, has a diameter of 6.5 meters, making it the largest telescope ever sent into space. JWST operates at a temperature of just 40 Kelvin, (-233 degrees Celsius), allowing it to detect faint heat signals from the most distant galaxies. Key instruments and capabilities. Near-infrared camera (NIR-CAM) captures high-resolution images and spectra in the near-infrared range, crucial for studying distant galaxies. Near-infrared spectrograph (NIR-SPEC) provides detailed spectral information, helping to determine the composition, temperature, and velocity of distant objects. Mid-infrared instrument (MIRI) extends the telescope's reach into the mid-infrared range, essential for observing cooler objects. Fine guidance sensor, near-infrared imager and slitless spectrograph (FGS, NIRISS) ensures precise pointing and captures slitless spectra for broad surveys. Discovery of Judas GSR 14-0. The observational campaign. The discovery of Judas GSR 14-0 was part of a larger observational campaign aimed at identifying and studying high-redshift galaxies. The team used JWST's NIRCam and NIR-SPEC instruments to conduct deep-field observations, focusing on regions of the sky known to contain candidate high-redshift galaxies. Spectroscopic confirmation. The identification of Judas GSR 14-0 was initially based on its photometric redshift, estimated from its colors in multiple infrared filters. Follow-up spectroscopic observations with NIR-SPEC confirmed the redshift of 14.0, providing a precise measurement of the galaxy's distance and age. Properties of Judas GSR 14-0. Judas GSR 14-0 is a relatively small galaxy, with a stellar mass estimated to be around 10^8 solar masses. It exhibits signs of intense star formation, with a star formation rate of approximately 10 solar masses per year. The galaxy's light is dominated by young, hot stars, indicating that it is in the midst of a vigorous period of star formation. Implications for cosmology and galaxy formation. The discovery of Judas GSR 14-0 has profound implications for our understanding of the early universe. It provides a glimpse into the conditions that prevailed just 290 million years after the Big Bang, offering valuable information about the formation and evolution of the first galaxies. Insights into early galaxy formation. The properties of Judas GSR 14-0 suggest that galaxies formed rapidly and efficiently in the early universe. The intense star formation activity observed in this galaxy indicates that the first galaxies were capable of producing stars at rates much higher than those seen in typical galaxies today. Constraints on theories of reionization. The detection of such an early galaxy also provides important constraints on theories of cosmic reionization. The high rate of star formation in Judas GSR 14-0 implies that early galaxies could have produced enough ultraviolet light to ionize the intergalactic medium, playing a crucial role in the reionization process. Challenges for theoretical models. The existence of a galaxy like Judas GSR 14-0 so early in the universe's history challenges existing theoretical models of galaxy formation. These models must now account for the rapid buildup of stellar mass and the efficient production of heavy elements observed in this galaxy. Future prospects and observations. The discovery of Judas GSR 14-0 is just the beginning. JWST is expected to uncover many more high-redshift galaxies, providing a more comprehensive picture of the early universe. Future observations will focus on obtaining more detailed information about the physical conditions in these galaxies and their environments. Deep field surveys. Deep field surveys with JWST will continue to push the boundaries of our cosmic horizon, revealing galaxies at even higher redshifts. These surveys will help to map the distribution of early galaxies and study their properties in greater detail. Spectroscopic studies. Follow-up spectroscopic studies will be crucial for understanding the chemical composition and physical conditions of high-redshift galaxies. By analyzing the spectra of these galaxies, astronomers can determine their metallicity, star formation history, and the presence of active galactic nuclei. The role of other observatories. While JWST will play a central role in studying the early universe, other observatories will also contribute valuable data. Ground-based telescopes, such as the Extremely Large Telescope (ELT) and the Giant Magellan Telescope (GMT), will complement JWST's observations with their own high-resolution capabilities. Conclusion. The discovery of Judas GSR 14-0 by the James Webb Space Telescope represents a monumental achievement in the field of cosmology. This galaxy, formed just 290 million years after the Big Bang, provides a unique glimpse into the early universe and offers valuable insights into the formation and evolution of the first galaxies. As JWST continues its mission, we can expect many more groundbreaking discoveries that will deepen our understanding of the cosmos and the processes that shaped it. Exploring the Cosmic Dawn. Further insights from Judas GSR 14-0. The environment of Judas GSR 14-0. The environment in which Judas GSR 14-0 formed is of great interest to astronomers. This galaxy's existence at such an early epoch implies the presence of significant underlying structure in the universe. Studying Judas GSR 14-0's surroundings can provide insights into the larger-scale environment in which the first galaxies emerged. Probing the intergalactic medium. One of the key aspects of studying high-redshift galaxies like Judas GSR 14-0 is understanding the state of the intergalactic medium, IgM, at that time. The IgM, composed mostly of hydrogen gas, was initially neutral after the Big Bang. The intense radiation from the first galaxies and quasars ionized this gas in a process known as reionization. By examining the spectra of light from Judas GSR 14-0, astronomers can detect the presence of absorption lines caused by neutral hydrogen. This allows them to infer the ionization state of the IgM and better understand the timeline and processes of reionization. The presence of significant neutral hydrogen absorption around Judas GSR 14-0 would suggest that reionization was still ongoing when this galaxy formed. Galaxy clusters and dark matter. The distribution of galaxies and galaxy clusters in the early universe provides clues about the nature of dark matter and the processes that lead to galaxy formation. Judas GSR 14-0's position relative to other early galaxies and clusters can reveal patterns in the distribution of dark matter. JWST's ability to observe multiple high-redshift galaxies in the same field of view allows astronomers to study the large-scale structure of the universe at these early times. By mapping the locations and properties of these galaxies, researchers can test theories of dark matter and the formation of cosmic structures. Star formation and stellar populations. Judas GSR 14-0's high rate of star formation is a crucial area of study. Understanding the mechanisms that drove such rapid star formation can shed light on the differences between early galaxies and those observed in the later universe. Stellar population synthesis. By analyzing the light from Judas GSR 14-0, astronomers can perform stellar population synthesis, a technique used to infer the properties of a galaxy's stars. This involves comparing the observed spectrum with theoretical models to determine the ages, masses, and metallicities of the stars. Judas GSR 14-0's spectrum reveals a population of young, massive stars, which are responsible for its intense ultraviolet radiation. These stars are typically short-lived, indicating that the galaxy is undergoing a significant burst of star formation. Additionally, the presence of heavy elements in the spectrum suggests that previous generations of stars have already synthesized these elements, enriching the interstellar medium.